Welcome to this walkthrough of problem number 1938, Maximum Genetic Difference Query. In this session, we'll explore the problem requirements, key concepts, and solution approaches. Let's dive in and tackle this problem together. In this problem, you're given a tree with n nodes labeled from 0 to n1 and a list of queries. Each query is represented as a pair, a node in the tree and an integer val. The task is to determine the maximum genetic difference between val and any ancestor of the given node. This includes the node itself. Now, the genetic difference is calculated using the bitwise XOR operation between two integers. The tree is described using a parent array, where each element indicates the parent of the corresponding node. The root node has no parent, so its value in the array is -1. Finally, the result for each query should be returned in the same order as the input queries. The output of the problem is a list of integers, where each integer corresponds to the maximum genetic difference for a specific query. Let's look at an example to understand this better. Imagine the parent array is defined as -1 0 0 1 1 2, which represents a tree structure rooted at node 0. The queries are 3 2 5 4 2 5. For these inputs, the output is 3 7 7. The explanation for these results depends on evaluating the tree structure and processing each query step by step. For the first query, 3 2, the ancestors of node 3 are nodes 3 1 and 0. The XOR values between val 2 and these ancestors are 1 3 and 2, respectively. The maximum is 3. For the second query, 5 4, the ancestors of node 5 are nodes 5 2 and 0. The XOR values are 1 6 and 4, with the maximum being 7. Finally, 4 2 5, the ancestors of node 2 are nodes 2 and 0. The XOR values are 7 and 5, and the maximum is 7. This example demonstrates how to compute the result for each query by considering the ancestors of the node and finding the maximum XOR value. In another example, the parent array is -1 0 1 2, which represents a tree with a single path from node 0 to node 3. The queries are 3 1 and 2 5. For the first query, the ancestors of node 3 include nodes 3 2 1 and 0. The XOR values with 1 are 2 3 0 and 1, giving a maximum of 3. For the second query, the ancestors of node 2 include nodes 2 1 and 0. The XOR values with 5 are 7, 4, and 5, resulting in a maximum of 7. This highlights how the tree structure directly influences the computation of XOR values for different queries. To solve this problem efficiently, we must consider the constraints. The number of nodes in queries can go up to 30,000, so we need an optimized approach to handle large inputs. Each node has a parent, with the root node being identified by -1. Queries involve nodes within the tree and values up to 2 to the power of 21. Several edge cases must also be addressed. For example, in a single node tree, the XOR value is simply val. For repeated queries targeting the same node, efficient computation is necessary. Special cases like val equals 0, where XOR simply returns the value itself, and the largest possible value of val must also be handled carefully to avoid overflow. These considerations will guide the implementation of a robust solution. To begin with, let's think about the brute force approach to solving this problem. The idea here is to process each query independently by iterating through all nodes in the tree. For a query consisting of a specific node and a value, we need to calculate the genetic difference between the value and all the ancestors of the given node. This genetic difference is determined using the XOR operation, and we return the maximum value from these computations for each query. The steps involve traversing the tree to find all ancestors of the node, which can be done using a depth-first search, either recursively or iteratively. For each ancestor, we calculate the XOR with the given value and keep track of the maximum result. However, this approach has significant computational overhead. With a time complexity of n*q, where n is the number of nodes and q is the number of queries, it becomes impractical for larger inputs. Additionally, it requires n space to store the tree representation, making it less scalable for complex datasets. However, the brute force approach has some clear drawbacks. It's highly inefficient when dealing with large trees and numerous queries because of its redundant computations. Specifically, traversing the tree for every query ignores opportunities to reuse previously computed results. This inefficiency highlights the need for a more sophisticated method. The optimized approach leverages a binary tree, which is a data structure designed to store numbers in their binary form. This structure allows us to perform XOR operations much more efficiently. Instead of traversing the tree repeatedly, the tree enables us to find the maximum XOR for a given value in O log m time, where m is the maximum value of the query's input. Key observations about XOR also come into play here. For instance, XOR's properties make it possible to determine the maximum genetic difference directly by navigating the tree. By combining the tree structure with the tree, we can process queries in a way that avoids the inefficiencies of the brute force method. To implement the optimized approach, we start by constructing the tree based on the given parent-child relationships. Next, we build a binary tree to store numbers in their binary representations. The algorithm then performs a depth-first search on the tree. As we visit each node, we add its value to the tree. For any queries associated with that node or its descendants, we compute the maximum XOR using the tree. After processing all queries for the current node, we remove its value from the tree before moving to its subtree. This ensures that the tree only contains values relevant to the current path in the tree. The time complexity of this approach is O, n plus q asterisk log m, where n is the number of nodes, q is the number of queries, and m is the maximum value of val. This is significantly better than the brute force method, especially for larger inputs. The space complexity is also efficient, requiring O, n plus log m, to store the tree in the tree. By leveraging the tree, we avoid redundant computations and achieve faster query processing. The tree-based optimization is the chosen strategy because it offers the best balance between efficiency and clarity. This method takes full advantage of the XOR operations properties and the tree structure, enabling significant performance improvements over the brute force approach. While it does require additional memory to store the tree, this trade-off is justified by the substantial speedup in query processing. The tree-based solution also comes with a slightly higher implementation complexity compared to brute force, but the benefits in terms of scalability and efficiency far outweigh the additional effort. Overall, this strategy provides a robust solution that handles large input sizes gracefully and avoids the pitfalls of redundant computations. By leveraging both the tree and the tree, we achieve a scalable and elegant resolution to the problem. To solve the maximum genetic difference query problem using the brute force approach, our first step is to understand the given data. The tree is represented by n nodes, where each node has an integer value. This tree structure can be stored as an adjacency list or edge list, which will help us navigate the relationships between nodes. Additionally, we are provided with queries, each in the format node val. Here, node refers to the specific node in the tree, and val is the value we are using to calculate the maximum XOR genetic difference. Next, we need to initialize our data structures. An adjacency list is ideal for storing the tree efficiently, as it allows us to traverse the child-parent relationships quickly. Alongside this, we should maintain a data structure, such as an array or dictionary, to store the value of each node for constant time lookups during query processing. Lastly, to prepare for efficient traversal, we pre-process the tree using a depth-first search, or DFS, starting from the root. This helps us determine the parent of every node and store these relationships in a parent array. For instance, parent I will give us the parent node of I, which simplifies moving up the tree later. Now that we've set up our tree in parent relationships, the next step is to process each query. For a given query, node, val, we begin by initializing key variables. The variable max_XOR is set to 0 and will be used to track the maximum XOR difference for this query. Starting at the specified node, we traverse up the tree to explore all its ancestors. At each step, we retrieve the value of the current node, compute the XOR difference between this value and val, and update max_XOR if the result is larger than the current maximum. We then move to the parent node, repeating the process until we reach the root where there are no more ancestors to consider. After completing the traversal for a query, the final max_XOR value is appended to the results list. This ensures that each query's result is stored for later retrieval. Once all queries have been processed, the results list is returned, providing the answer for every query in the input. To better understand why this approach works, let's consider some key insights. The XOR operation is fundamental here, as it highlights the bits where two numbers differ. To maximize the XOR result, we are essentially looking for an ancestor node whose value has the most differing bits compared to the given val. The brute force approach ensures that we traverse all possible ancestors of the given node, leaving no potential XOR combination unexplored. To optimize this process, the parent array is pre-computed so that we can directly navigate up the tree in O(h) time, where h is the height of the tree. Efficient data structures like an adjacency list are also critical. This representation of the tree is both space-efficient and allows us to traverse child-parent relationships seamlessly. For example, in a tree represented as 0, 1, 2, 1, 3, 4, 2, node 0 is the parent of nodes 1 and 2, and node 1 is the parent of nodes 3 and 4. This structure is simple yet powerful for managing tree traversal. In addition to the adjacency list, the parent array plays a crucial role in making our algorithm efficient. This array stores the parent of each node, allowing us to directly move up the tree during query processing. For instance, if parent equals -1, 0, 0, 1, 1, we know that node 1 and node 2 have parent 0, while nodes 3 and 4 have parent 1. Together with the parent array, we also use a dictionary to map node indices to their values. This ensures that we can quickly retrieve a node's value during traversal. For example, node_values equals 0, 5, 1, 3, 2, 8, 3, 6, 4, 7 means that node 0 has a value of 5, node 1 has a value of 3, and so on. With these data structures in place, we can focus on two main operations: constructing the tree and processing the queries. Tree construction involves building the adjacency list and parent array through a single DFS, which takes O(n) time. Query processing, on the other hand, involves traversing the ancestors for each query. In the worst case, this requires visiting all levels of the tree, resulting in O(h) time per query. For Q queries, the total complexity is therefore O(q*h). Finally, let's analyze the space complexity and address some edge cases. The adjacency list, parent array, and results list together require O(n plus q) space, which is efficient given the problem constraints. As for edge cases, consider a single node tree. In this scenario, all queries will compute the XOR using only the root node's value, making it a straightforward case. For deep trees, where the height is significant, query processing may slow down due to the number of ancestors that need to be traversed. However, the algorithm still guarantees correctness. Duplicate values in the tree do not pose an issue, as the XOR operation is purely value-based. Lastly, the algorithm is designed to handle large inputs, such as trees with up to 10,000 nodes and queries, ensuring it remains efficient even at the upper limits of the constraints. To implement the solution, we start by defining a tree structure which will help us efficiently manage the numbers and their binary representations. First, we define a tree node class. Each tree node will maintain its children in a dictionary and keep track of a count, which will help us manage the number of insertions at each node. Next, we define the tree class itself. The tree has a root node, which is an instance of tree node. The insert method is used to add a number into the tree. For each number, we iterate through its binary representation, from the most significant bit to the least significant bit. At each bit, we check if the corresponding path exists in the tree. If not, we create a new tree node. We then move down that path and increment the count at each node. Similarly, we define a remove method to decrement the count along the path of a number when it's no longer needed in the tree. This allows us to dynamically manage the tree as we process the queries. Now, we add a method to the tree class called max_XOR. This method calculates the maximum XOR value between a given number and any number currently stored in the tree. For each bit of the number, we attempt to traverse the path that would maximize the XOR, which is the opposite of the current bit. If this path exists and has been inserted into the tree, we update the max_XOR value and traverse down that path. If not, we proceed down the path of the current bit. This ensures that we always find the maximum possible XOR. Next, we move to the solution class, which implements the main logic for solving the problem. We begin by constructing the tree structure from the given parent-child relationships. Nodes with a parent of -1 are identified as the root. For the queries, we group them by the node they are associated with, using a dictionary where the key is the node and the value is a list of queries related to that node. This organization allows us to efficiently process the queries during traversal. To solve the problem, we initialize the result list to store answers for all the queries and instantiate the tree. We then define a depth-first search (DFS) function, which will traverse the tree starting from the root node. For each node, we first insert it into the tree. Then, for every query associated with the current node, we calculate the maximum XOR value using the max_XOR method and store the result in the corresponding index. After processing the queries for the current node, we recursively call DFS on each of its children. Once all the children have been processed, we remove the current node from the tree, ensuring that the tree remains clean and relevant for other branches of the traversal. Finally, we invoke the DFS function on the root node and return the result list, which contains the answers to all the queries. Here, we start by defining our tree node class, which represents a single node in the tree data structure. Each node contains a map called children to store its child nodes, where the key is the bit value, either 0 or 1, and the value is the corresponding tree node. Additionally, there is a count variable to track how many numbers pass through this node. Next, we define the tree class, which includes an instance of the root node. In the insert method, we add a number to the tree by iterating through its binary representation from the most significant bit to the least significant bit. For each bit, we check if the corresponding branch exists in the tree, and if it doesn't, we create a new tree node for that bit. Finally, we move to the next node and increment its count, ensuring the tree structure is updated with the new number. The remove method allows us to delete a number from the tree. Similar to insertion, we traverse the tree using the binary representation of the number. At each step, we move to the appropriate child node based on the current bit and decrement its count. This ensures the count reflects the removal of the number. The maxor method computes the maximum XOR value for a given number using the tree. As we traverse the tree, we attempt to follow the branch that differs from the current bit, as this maximizes the XOR result. If the opposite branch does not exist or has a count of 0, we follow the branch matching the current bit. Throughout the traversal, we update the maxor variable by setting the appropriate bits, and at the end, we return the maximum XOR value. We now move on to the implementation of the solution class and the max genetic difference method. First, we build a tree representation of the parent-child relationships using a hash map. Nodes with no parent, indicated by a value of -1, are identified as the root of the tree. Next, we organize the queries by the node they are associated with, storing each query as a pair of the value and its index in the result array. We then initialize the result array to store the answers to all queries and create a tree instance. To process the queries, we call the DFS helper method, which performs a depth-first traversal of the tree. This method will handle inserting nodes into the tree, calculating results for queries, and removing nodes as we backtrack. In the DFS method, we start by inserting the current node into the tree. If there are any queries associated with this node, we process each one by calculating the maximum XOR value using the tree's maxor method. The results are stored in the appropriate indices of the result array. Next, we recursively visit the child nodes of the current node to continue the traversal. After all child nodes have been processed, we remove the current node from the tree to ensure it does not interfere with calculations for other parts of the tree. This ensures that the tree always represents only the nodes in the current path of the traversal. Finally, the results array is returned, which contains the maximum genetic difference for each query. In this example, we are given a simple tree structure and a single query. The input specifies that node 0 is the root because its parent is -1, and nodes 1 and 2 are its children. The resulting tree is a small binary tree with node 0 at the top and nodes 1 and 2 as its children. The query asks us to calculate the maximum XOR between the number 2 and the values in the ancestry of node 1. To manage this, we map the query to the corresponding node, resulting in a query mapping of queries_by_node equals 1, 2, 0. We then use a depth-first search (DFS) strategy combined with a tree data structure to process this query efficiently, as the tree allows us to compute XOR values quickly during traversal. Starting with the DFS and tree operations, we first visit node 0, which is the root. Here, we insert the value 0 into the tree, which initializes the tree with the root node. Next, we traverse to its children. At node 1, we insert the value 1 into the tree, updating its state to represent the path from 0 to 1. Now, we process the query 2, 0, which asks for the maximum XOR of the number 2 with the values in the ancestry of node 1. To answer this, we calculate the maximum XOR of 2 by traversing the tree. The binary representation of 2 is 00010, and using the tree, we maximize the XOR to obtain a result of 3. We store this result in the result array at index 0. After processing the query, we remove the value 1 from the tree as we backtrack. Then, we move to node 2, insert its value 2 into the tree, and remove it once we're done processing. After finishing the traversal of node 2, we backtrack to node 0 and remove its value from the tree as well, completing the DFS. The final output for this example is result equals 3, indicating that the maximum XOR for the given query is 3. Now, we move on to a larger example with multiple queries and a more complex tree structure. For this new example, the input specifies that node 0 is the root, and the tree structure is more expansive, with nodes 1 and 2 as children of node 0. Nodes 3 and 4 are children of node 1, while node 5 is a child of node 2. This results in a tree with depth and branching, which we will use to process multiple queries efficiently. In this larger example, we start by mapping the queries to their respective nodes. The queries _by_ node dictionary is created as follows. Node 3 has the query 5, 0, node 2 has the query 1, 1, and node 5 has the query 4, 2. With the queries mapped, we proceed with the DFS and tree operations. At node 0, we insert the value 0 into the tree and then traverse to its children. At node 1, we insert the value 1 into the tree and continue the traversal. At node 3, we insert the value 3 into the tree and process the query 5, 0. Using the tree, we calculate the maximum XOR of 5, which results in 6. This value is stored in the result array at index 0. After processing, we remove the value 3 from the tree. Then, at node 4, we insert the value 4 into the tree and remove it once done. After finishing with node 4, we backtrack and remove the value 1 from the tree. Next, we move to node 2 and insert the value 2 into the tree. Here, we process the query 1, 1, which asks for the maximum XOR of the number 1. Using the tree, we calculate this value to be 3, and we store it in the result array at index 1. Moving on to node 5, we insert the value 5 into the tree and process the query 4, 2. Calculating the maximum XOR of 4 results in a value of 1, which is stored in the result array at index 2. Once the query is processed, we remove the value 5 from the tree. Finally, we backtrack to node 2, remove its value from the tree, and then backtrack further to node 0, removing its value as well. This completes the traversal of the tree, and the final output for this example is result equals 6, 3, 1. In the edge case example, we are given a tree consisting of a single node, node 0, which is the root as its parent is -1. The tree structure is minimal, containing only node 0. The input also specifies a single query, 0, 7, which asks for the maximum XOR of the number 7 with the values in the ancestry of node 0. Since node 0 is the only node, it is the only value available for the XOR calculation. We map this query to the root node, resulting in queries _by_ node equals 0, 7, 0. Using the DFS and tree operations, we start at node 0, insert its value 0 into the tree, and process the query 7, 0. Calculating the maximum XOR of 7 with the numbers in the tree yields a result of 7, which is stored in the result array at index 0. After processing, we remove the value 0 from the tree. With the processing complete, the final output for this edge case example is result equals 7. This demonstrates that even in the simplest tree structure with a single node, the algorithm effectively calculates the maximum XOR for the given query. This concludes the solution walkthrough. where we've explored examples ranging from simple trees to complex structures and edge cases, demonstrating the efficiency and correctness of the DFS and tree-based approach for solving the maximum genetic difference query problem. The time complexity of solving this problem can be analyzed by breaking it down into specific operations. First, we have the task of building the tree structure. This is done using the parents array, which allows us to construct the parent-child relationships for all nodes in the tree. Since we are iterating through the parents array, and its size is determined by the number of nodes, n, this operation requires n time. Second, we process the queries. Each query is tied to a node and grouped into a queries_by_node data structure. With m queries in total, we iterate through the queries array, making this step take m time. These two steps lay the foundation for the solution's time complexity analysis. The next part of the time complexity analysis involves the depth-first search, or DFS, traversal of the tree, which handles the bulk of the computation. For each node number, we insert it into the tree. This insertion process involves traversing 18 bits, because numbers go up to 10 to the power of 5, which can be represented in 17 bits, plus one additional bit. Since this is a fixed number of bits, the time complexity per insertion is 18, which simplifies to 1. Similarly, when processing a query, val idx, at a node, finding the maximum XOR in the tree also requires traversing these 18 bits, making the query operation 1. Removing a node from the tree after backtracking works the same way as insertion, also taking 1 time. Over the entire DFS traversal, each node is inserted and removed exactly once, and each query is processed. Therefore, the total time complexity for the DFS traversal is n, for the nodes plus m, for the queries, giving us a total of n plus m. Now let's analyze the space complexity of the solution, starting with the tree structure. The tree is represented as an adjacency list, which is implemented using a default dict. For n nodes, the space required is proportional to the number of edges, which is n. Next, we consider the space used by the queries_by_node dictionary. This dictionary groups up to m queries based on their associated nodes, and thus requires additional space of m. Together, these two components contribute n and m to the total space complexity, respectively. The tree structure is another important component of the space complexity. During the DFS traversal, the tree stores all nodes that are part of the current path. Each number is represented in binary with 18 bits, and each bit can branch into two children, either 0 or 1. In the worst case, the tree can have up to n nodes, with a maximum of 2 by 18 n pointers, because each level of the tree could potentially have two branches. This results in a space complexity of 18 n, which simplifies to n. Additionally, we have the result array, which stores the answers for all m queries, contributing m to the space complexity. When we combine the contributions of all components, the tree structure, queries, tree, and result array, the total space complexity is n plus m. To better understand the efficiency of this approach, we can compare it to a naive method. In a naive approach, for each query, you would compute the maximum XOR by traversing all the ancestor nodes of the given node. This repetitive traversal of the tree for each query leads to a time complexity of m*h, where h is the height of the tree. In the worst case, such as with a skewed tree, h can be as large as n, resulting in a total time complexity of m*n. In contrast, the optimized tree-based approach reduces the total time complexity to n plus m. This is because the tree allows us to compute the maximum XOR for each query in 1 time, while insertion and removal operations for each node also take 1. Thus, the tree-based approach is significantly more efficient, especially for large inputs. Let's now analyze the algorithm across different scenarios: best, average, and worst cases. In the best case, where the tree is shallow and the number of queries is small, the algorithm operates in n plus m time and uses n plus m space. In the average case, with a balanced tree and queries evenly distributed across the nodes, the algorithm still performs in n plus m time. The tree structure is used efficiently, keeping the space complexity at n plus m. Even in the worst case, with a highly unbalanced tree and a large number of queries, the tree might grow significantly due to its branching structure, but the algorithm's time complexity remains n plus m, with space complexity also staying within O, n plus m. This consistency in performance across all cases highlights the robustness of the solution. To conclude, let's summarize the proof of the algorithm's overall big O complexity. Each node is processed exactly once during insertion and once during removal, contributing O, n, to the total time complexity. Additionally, each query is processed in O, 1, time, leading to an O, m, contribution. Tree operations, whether for insertion, removal, or querying, are bounded by the number of bits, which is fixed at 18. This makes these operations effectively O, 1. Combining these components, the overall time complexity is O, n plus m. On the space side, the tree structure, queries, and tree collectively contribute O, n plus m, space. Thus, the solution is both time and space efficient, scaling well with the size of the input. When solving this problem, there are a few common mistakes to watch out for. First, not handling edge cases can lead to runtime errors or incorrect outputs. For instance, in scenarios where the tree has only one node or is empty, your code must account for these possibilities rather than assuming the presence of ancestors. Additionally, an inefficient traversal strategy can significantly hurt performance. If you're recomputing values for every query using a brute force approach, this can lead to a time complexity of O, n squared, or worse, which is impractical for larger inputs. Instead, you should focus on leveraging pre-computation techniques to eliminate redundant calculations. Another frequent issue is incorrect ancestor identification. This can happen if you misunderstand the tree structure or fail to properly traverse to the correct nodes. A robust parent-child mapping is essential for accuracy. Lastly, mismanaging bitwise operations, such as XOR, is another potential pitfall. Always ensure you're applying these operations correctly, paying attention to operator precedence and understanding how XOR behaves, particularly with values like 0. Now, another mistake to avoid is overcomplicating the problem. Sometimes, you can simplify your approach by recognizing patterns like lowest common ancestor or leveraging the properties of bitwise operations. Over-engineering your solution can introduce unnecessary complexity, making it harder to debug and more prone to errors. On the topic of interviews, it's important to understand tree traversal patterns. Depth-first search and breadth-first search are foundational techniques for tree problems, so you should be comfortable implementing both iteratively and recursively. Pre-computation is another key optimization strategy for problems involving multiple queries. By pre-computing data, such as ancestor relationships or XOR values, you can significantly reduce redundant calculations during query processing, which can dramatically improve time complexity. Lastly, make sure you can clearly explain the trade-offs between brute force and optimized approaches. For example, while pre-computation increases memory usage, it can drastically reduce the time required to handle each query. Being able to articulate these trade-offs is highly valued in interview settings. It's also crucial to test edge cases thoroughly. For instance, ask clarifying questions about edge scenarios like trees with only one node, highly unbalanced trees, or specific constraints on node values. These details can impact how you design your solution. Additionally, understanding related problems can deepen your ability to recognize patterns and apply transferable skills. For example, LeetCode 236, which focuses on finding the lowest common ancestor of a binary tree, is directly relevant for ancestor-based problems. Similarly, LeetCode 1483, which deals with the kth ancestor of a tree node, emphasizes pre-computing data for efficient queries. LeetCode 543, which involves calculating the diameter of a binary tree, strengthens your grasp of DFS and tree traversal. Finally, even though LeetCode 1319 is not a tree problem, its focus on graph traversal and efficient computation can improve your problem-solving skills, as both tree and graph problems often share similar concepts and techniques. There are several alternative approaches you can consider to optimize your solution further. One common strategy is using an optimized DFS with pre-computation. For example, you can pre-compute ancestor relationships or XOR values for each node, which allows you to achieve constant or logarithmic query time, although this comes at the cost of pre-processing time. Another powerful technique is binary lifting for ancestor queries. If the problem involves repeated ancestor lookups, binary lifting can reduce query complexity to O log n, while keeping pre-processing at O n log n. For problems involving range queries or updates, you might also consider using a segment tree or Fenwick tree. These structures are highly efficient for such operations, though they can increase the implementation complexity. Lastly, if the problem involves XOR or other bitwise manipulations, leveraging bitwise tricks can simplify your logic. For example, taking advantage of properties like a XOR A equals 0 can eliminate redundant operations and improve clarity. By understanding and applying these techniques, you can tailor your solution to different variations of the problem effectively. Great job completing this session. We covered the key ideas behind solving maximum genetic difference query, including leveraging tries for optimization. Remember to practice similar problems to solidify your understanding. Thank you for watching, and we'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!